Okay, hi everyone. This is our last video lecture on the postulates of quantum mechanics. Postulate 5 says it is impossible to simultaneously specify with arbitrary precision both the position and momentum of a particle. The uncertainties in position and momentum, delta x and delta p, are governed by this equation here. And this idea is incredibly important. It's so important that it's given its own name, which is Heisenberg's uncertainty principle. I hope you may have heard of this before. You may know something about it, and I'll describe it to you. But before I do that, I wanted to tell you briefly about Heisenberg. He was one of the original formulators of quantum mechanics. And in particular, he developed a formalism using linear algebra and matrices. At the same time, Schrödinger was using his differential equation version. And it turned out that these were entirely equivalent. So he basically developed his own version of quantum mechanics. He won the Nobel Prize in physics in 1932. And interestingly, he was the leader of the German nuclear bomb project. There's some really interesting history here. So I hope that you know that the United States developed the atomic bomb before the Germans did. That was called the Manhattan Project. And people ask why the Americans got this done before the Germans. And one answer might simply be that the American scientists were better. However, other people say, you know what? Heisenberg was pretty smart. And if he wanted to, he probably could have developed the technology and the science to build these bombs. One of his graduate students was Niels Bohr, who was a Danish Jew. And in some letter correspondence, it looks like Heisenberg may have been intentionally sandbagging the German efforts. Right? At the same time, he was clearly involved in this. And so there's this interesting uncertainty about his role in this whole thing. This is described beautifully in a play called Copenhagen. And if you ever get a chance to see it, check it out. So, first thing I want to tell you about Heisenberg's uncertainty principle is that it is not a statement about our ability to make a measurement. This is the most common misunderstanding about the uncertainty principle. Heisenberg was not saying that we can't make a good measurement. In 100 years, when the instrumentation is much better and Siri is much smarter, we will not be able to make any measurement beyond the Heisenberg limit. It's also not a statement that you can't know position and momentum. Like thermal, small words here make a big difference. So what the principle is saying is that you can't know them at the same time with perfect precision. There's a limit on the knowledge. And in this type of equation, these two variables are complementary. So what you'll see is that if one of them is maximized, the other one is minimized, right? And vice versa. They're balanced. What this is really saying is that there is a fundamental limit on the precision of our knowledge. And this is really another interesting philosophical point. In classical physics, if you know the equations of motion and the starting position and velocity, you can calculate it at any time later. Heisenberg's principle is saying that's not true because I can never know precisely what the position and momentum are. And where does this all come from? Well, at the end of the day, it ultimately originates from the wave-particle duality of nature. All right, let's dig into this a little bit. There's a specific quantitative meaning to the uncertainty principle. Delta x and delta p, the uncertainties in position and momentum, have specific mathematical definitions, and those are given here. So note that when you see these types of brackets, these are expectation values. So you can use the formalism for calculating expectation values from postulate 4 to calculate these. you calculate them, you insert them into the equation, and you will get a result consistent with the uncertainty principle. And as I'm just looking at these equations now, I realize that there is a mathematical error in it. So I'm going to fix it. Right? It is delta x, this quantity raised to the 1/2 power. And this one's raised to the 1/2 power. I could hear you screaming over the internet that I had a units problem. That had to be wrong. All right, those are the mathematical definitions of those things. And you'll do some of this on the homework. You'll mathematically calculate these things and show them to be true. I think it's equally interesting and perhaps more insightful to think about qualitative interpretations. And so the question is, what do you associate with the uncertainty in the position and the uncertainty in the momentum of a particle? And I think the easier of these two is the uncertainty in position. You might buy that the uncertainty in position is related to the width of a wave function. We interpret squares of wave functions in terms of probability, and this one is spread out in space more than this one is. Right? And so in this example, the uncertainty in this wave function, delta x1, is bigger than the uncertainty in this wave function. Delta x1 greater than delta x2. Now, from this result by itself, you can make some inferences. Right? Remember that x and p are complementary. So when one of these variables, when the uncertainty in position is maximized, uncertainty in momentum is minimized. And because I know that delta x1 is greater than delta x2, I can make an argument, right? From this statement, I know that delta p2 must be greater than delta p1. Okay? If delta x1 is big, delta p has to be small. And if delta x is small, delta p has to be big. So these are complementary. And in fact, you can start to tie this together with other ideas that we've seen in class. So the momentum is associated with the wavelength of a wave function. Right? This was emphasized in the de Broglie relationship. Right? P is equal to h over lambda. This wave function has a large wavelength. Right? This one has a smaller wavelength. If that's true, this one, I can't write. This one has a small momentum. This one has a large momentum. And if it has a large momentum, it will have a large delta P. This one will have a small delta P. So qualitatively, the width of the wave function is related to its uncertainty in position. The wavelength is related to the uncertainty in momentum. And I'll just show you one last example of that. This is hashed out a little bit more quantitatively. These are called wave packets. It's the way we actually think about photons and quasi-particles. What these are a linear combination of sine curves of varying wavelength. So the number here will tell you about the number of sine curves that are in the superposition. Right? This one has 2, this one has 5, this one has 21. And you can see there are two opposite effects. So I should say this. A sine curve has a very definite wavelength, right? You could determine it. If this one only has 2 sine functions in the superposition, it has a relatively small uncertainty in its wavelength. Whereas this one has 21 sine curves in the superposition. So this one would have a large delta P. And just as you would expect, if this one has a small uncertainty in momentum, because there's a small number of sine curves, it has a large delta P. I said P, but I meant X. This one has a large uncertainty in position. Whereas this one, with 21 sine curves, becomes highly localized and has a much smaller uncertainty in position. All right, we'll see that at various times throughout the course. And now you know all the rules of the game. We'll start applying them in the next set of videos. See you then.